Welcome back to Data Explained channel, where we make complex topics easy to understand. Today we talk about data boundaries, range limits. Every data representation operates within defined boundaries. One of the most fundamental of these boundaries is range. Range limits describe the minimum and maximum values that a data representation can express. Anything outside that range cannot be represented and must be handled through approximation, truncation, or failure. These limits are not optional. They are an unavoidable consequence of finite representation. Digital systems store data using a fixed number of bits. With a finite number of bits, only a finite set of values can be encoded. The size of that set directly determines the representable range. For example, an unsigned 8-bit integer can represent values from 0 to 255. A signed 8-bit integer can represent both positive and negative values, but at the cost of a smaller positive range. As more bits are allocated, the representable range increases. However, storage, transmission, and processing costs also increase. Range is therefore always a design trade-off. Range limits appear in all numeric representations. Integers have strict upper and lower bounds. Floating point numbers provide extremely large ranges, but they do so by sacrificing precision at different magnitudes. Fixed point representations limit both range and resolution in predictable ways. When values exceed representable range, systems must respond. This response may involve overflow, underflow, saturation, clipping, or error signaling. Each behavior has different consequences, and none are neutral. Overflow can cause values to wrap around, producing results that appear valid but are fundamentally incorrect. Underflow can collapse values to 0, silently discarding information. Saturation clamps values at fixed bounds, preserving stability but losing magnitude information. Range limits are not confined to numeric data. Timestamps are limited by epoch definitions and bit widths. Counters roll over. Identifiers exhaust available values. Even categorical encodings can run out of representable states when assumptions change. In long-running systems, range limits become especially dangerous. A system may function correctly for years before encountering an extreme value. When that boundary is crossed, failures can appear suddenly and unpredictably. Many real-world system outages trace back to unanticipated range exhaustion. Range limits also influence modelling and analysis. If extreme values are clipped or excluded, distributions become distorted. If ranges are mismatched across systems, data may be silently truncated during integration. If assumptions about scale are incorrect, conclusions may be invalid. Understanding range limits means understanding what data cannot express. It requires identifying worst-case scenarios, growth patterns, and edge conditions. It requires designing representations that remain valid not only today, but under future conditions. Range limits are not abstract constraints. They are practical boundaries that shape system behavior. Professional data design acknowledges these limits explicitly, tests them deliberately, and documents them clearly. Because when range limits are ignored, failure is not a question of if, but when.